thank you, Ken. Thanks for that generous introduction, and good evening to you all. It's wonderful to be here in Pensacola. This is my first trip to Pensacola, and I was looking very much forward to it when about 6 months ago, Ken invited me to come and visit with you all. I've been very impressed with the city, with this institute, and the friendliness of you all here. It's been great. So I do have some southern roots, so they'll come out now and then. Well, tonight what I'd like to do is to tell you a little bit about our new center that we have developed called LUNAR, the Lunar University Network for Astrophysics Research. About 2 years ago, NASA formed a new institute itself called the NASA Lunar Science Institute, and it's located in the Ames Research Center in Palo Alto, California. And in turn, they put out a call for proposals about 1.5 years ago for university affiliates or university centers. Very high, stiff competition. We were fortunate to be one of the 7 university centers that was chosen. And we're the only one dedicated to the pursuit of astronomical observatories on the lunar surface. And so what I want to do tonight is to tell you about some of the unique facilities that we are planning, both in the short term as well as the longer term, on both the near side and the far side of the moon. Ken mentioned that our lunar facility is headquartered in Boulder at the University of Colorado, but very importantly, you see the logos down over here. These are the many institutions that are affiliated with us. We have over 40 individuals from places, NASA centers such as the Goddard Space Flight Center, the Jet Propulsion Lab, Harvard University, MIT, UCLA, the National Radio Astronomy Observatory, and the Naval Research Lab, just to mention a few who are involved in this work. Well, humans have been interested in the moon probably as far back as folks started looking up in the sky and wondering what that big bright ball was hanging there in the sky. It's far and away the brightest object in the nighttime sky. It's the only one that you can really resolve well with the human eye. Classic science fiction has been written about the moon. You go back to Jules Verne in the 18th century, 19th century, I should say, 20th century, you had H.G. Wells. And beginning in the 1950s, there was also some really interesting science fiction movies that began to appear about the moon. Here is probably one of the best, I think. This is called Destination Moon, 1950, 60 years ago. People were talking about trips to the moon, and here's just a couple of frames from that movie, and really not too bad of a job in capturing some of the features and so forth. What they did miss is the fact that on the surface of the real moon is about 2 centimeters, a few inches or so of dust, which is present everywhere on the moon, and probably is the kind of feature also that you will see in asteroids when we eventually get there as well. So a number of such movies, some fairly serious like Destination Moon. Others, well, not quite as serious. Catwomen of the Moon, 1953. You've never seen anything like it. That's probably true. Love-starved moon maidens on the prowl. Here's something interesting. Music by Elmer Bernstein. Anybody recognize that name? Yes, he composed some Academy Award-winning music. Not in this movie. He was clearly slumming when he was doing this. I actually have a little clip for you of this movie that I want to play for you. It's a trailer for the movie in 1953. Just kind of fun to take a look at, see what we were thinking then. Never seen this kind of woman before. Without men for centuries. How do they procreate?
Where are your menfolk?
You're the first man I've ever seen.
3D. Okay, James Cameron, he thinks, Avatar is special on 3D in 1953. Look at the interior of the spaceship. You know, they're supposed to be in 0G, but they don't seem to be having trouble putting the makeup on there. And of course, the Hollywood cover girls. Who else would you choose?
Ellen, what's the matter?
Danger, Kip. They want to kill you. They'll take the spaceship and they'll make me go with them.
Great acting in here, too.
They can, Kip. They control me.
You'll share man's greatest thrill as you rocket through space to the lost moon city of alluring, ferocious cat women. Theirs is the fevered fury of life without love, goading them to lure men into the den of bloodthirsty moon monsters.
We missed those with Apollo.
To tempt men in the
I bet they are hidden
cave of
underground
moon gold,
somewhere in these
flaming
lava
into a
tubes.
wild lust to conquer man and
Ooh,
destroy
that's gonna leave a
the
mark.
world.
Yikes. Oh, rough. Most startling picture of the century. I believe that's true. Wow. No, I don't know how many of you have seen Catwomen. Probably don't remember it if you did see it. But, so, of course, we did go to the moon successfully. In 1969, we fulfilled John Kennedy's vision to go to the moon and return back safely by the end of the decade. He proclaimed this in 1961, just literally weeks after Alan Shepard's first suborbital mission. It was astounding. Vision that was set forward and the technology leap that was required to get there. But indeed, in 1969, we celebrated the 40th anniversary just this last summer, set foot on the moon. Here was the landing vehicle that I've superimposed above the surface of the moon. A couple of the astronauts on their lunar buggy, one here. And this is Jack Schmitt. I show this picture because Senator Schmitt, who's actually, when he finished off, became senator from New Mexico, was a PhD, is a PhD in geology, the only scientist astronaut to go to the moon. I think people understand certainly that Apollo was a great success in many different ways. Number one, of course, it was a political success. The idea was to beat the Russians to the moon. It was the middle of the Cold War. That was successful. The second way that it was successful is that for human exploration, we broke the bonds of low Earth orbit and went in just a few years all the way to the surface of the moon and stepped foot on another astronomical body. Clearly that was a pioneering breakthrough that we have not duplicated in almost 40 years. The third thing that was very important as part of what I want to emphasize tonight was it was a scientific success as well, because the data, the rock samples, the core samples, other data that was brought back from Apollo was absolutely crucial in determining how the moon was formed. Today we know that the moon was actually formed about 4.5 billion years ago as a result of a collision between an early Earth and a Mars-sized body. Not Mars, but a Mars-sized asteroid. It collided with the Earth, vaporized that large asteroid, and the moon formed out of the debris, the combination of residue from the Earth as well as that asteroid. Because the moon is neither the Earth nor looks like the asteroids, it's really a combination. And so that data was crucial. Why is that important? That's because we're talking about our home world was greatly influenced by the fact that we have a moon today as well as in that early history. And our history of our planet is a history of collisions and bombardments. It's fundamentally changed. 65 million years ago, we had a large asteroid or set of asteroids struck the Earth, killed the dinosaurs. We wouldn't be here today. We'd all be dinosaurs up here instead with big tails and floppy things and walking around like that. No, but seriously, it fundamentally altered. And the moon is important, continues to be important today because it has uniquely recorded that history of bombardment, which on the Earth has been wiped out by millennia, by millions of years of erosion by water and air. So the moon continues to be a crucially important astronomical body in which we can learn about ourselves and our history. Here are the landing sites for Apollo, 6 landing sites, as you'll recall, all of them in more or less the equatorial zone of the front side of the moon. As many folks probably recognize, one side of the moon always faces the Earth. The other side, called the far side, not the dark side, there is no dark side, because all sides of the moon receive light as well as a nighttime. But the far side of the moon always faces away. It's what astronomers call tidally locked. And we only explored these regions of the moon. The Russians put a couple of unmanned craft down over here called Luna that sent back some rock samples as well. But this is it. It's pretty limited. So when I hear people say, you know, we've been to the moon, we've done everything there is, you know, the moon is so 1960s, let's just go to Mars. Well, you know, we have hardly sampled the moon. It's kind of like Lewis and Clark coming back from their 2-year expedition up the Missouri River, going all the way to the West Coast and to Oregon, coming back, and with a detailed report for Thomas Jefferson of the fish they caught and the Native Americans that they interacted with. And Jefferson read this and says, yep, we now know everything there is about the American West. No reason to go back. Let's just shut the gates. Okay? That's kind of what we've done with the moon, but not recognizing that the moon is, in fact, our library of the solar system. With Apollo, we went into that front door of the library, thumbed through a few of the magazines at the front, and then left. Back in the library, further in, are the big books, the stacks, where you open up and the history of the solar system, the history of our sun through its radiation and solar wind that's been captured on the surface, as well as the bombardment history of the moon, tells us who we are and how we got here, the most fundamental questions. That's right there on the moon. It's not easy to capture that information at all on the Earth. So when people say, you know, we've been there, done that on the moon, I say, not by a long shot. We need to indeed go back to that library. Well, here's pictures of the near side of the moon, the side we're used to looking at. We can see it pretty well with a small telescope. Here's the far side that we can only see with satellites. One of the first things you notice is how different the far side is from the near side. In fact, this is not well understood today. The near side, the far side, I should say, has more of these what are called highlands. They're elevated above the surface, whereas the near side has all of these dark regions called maria, which are flooded impact craters, flooded by lava. Billions of years ago, actually, this occurred. Why are those two sides different? And why is the center of the moon actually located, the balance point, the center of the mass of the moon, is actually closer to the Earth than the geometrical center of the moon? Those are really basic questions that we still don't understand very well. Let's take a little look at the Earth-Moon system as seen from space. I have a nice little video that we have put together using some new software that was developed by a little company in Golden, Colorado. These are actual images now of the Earth seen from space. This is just amazing to think this is our planet. This is a reflection of the sun, as you see in this particular view. So there's Australia, and you see India coming up over here, and Africa. The thing that you notice is how thin our atmosphere is. I mean, you can hardly make out that there's an atmosphere there. And how precious that atmosphere is, because that's, of course, necessary for life. Looking back towards the sun, you have a little bit of the Earth here, and we're going to be coming up to the moon. The moon is only 3 days away. I say only 3 days away because if you want to go to Mars, it takes 6 months to get to Mars. You spend a year on its surface, and then 6 months coming back before you are through. The 2-year mission to the moon, 3 days. Here's the far side of the moon, now a little rotation. Again, I show this because I'm going to be focusing a little bit later on the far side, because that's where we would like to put our low-frequency radio telescopes, because it's the only truly radio-quiet place in the inner solar system. So we're spinning around here looking a little bit more at that side of the moon you don't see very often. Now here's a comparison between, again, the near side and then back to the far side. So once again, you can see it's dramatically different between those two surfaces of the moon. We'll just flash that one more time again for emphasis. Now, I showed you the locations of the 6 sites where the Apollo astronauts landed. I'm going to argue now in just a few minutes that we didn't even go to the most interesting places on the moon. The interesting places, I think, today are the poles. This is a look at the south pole of the moon. There's some really interesting and exciting developments that we didn't appreciate during the Apollo era. But in the last few years, as a result of a flotilla of new spacecraft that have returned to the moon, let me just get rid of this here, that a flotilla of international spacecraft, we've begun to learn a lot more about the moon. We have indeed returned to the moon, but it's just not with humans. There are spacecraft from China, from India, from Japan, and from the United States in the last 2 years have all gone into orbit of the moon and begun taking crucial scientific data with modern instruments that we didn't have during the Apollo era. We haven't been back mostly to the moon, with the exception of a couple of spacecraft in 35 years. So this is an exciting development. With those new detectors, we have begun to make some pioneering discoveries that we had not expected. Here is an example. This is a US spacecraft. It's actually a two-component spacecraft. There's one, is the Lunar Reconnaissance Orbiter, and carried along with it was something called LCROSS. Now, LCROSS is a little satellite here, and what it did is it guided the upper stage of the rocket that launched it and LRO, and it guided it to the moon and crashed that rocket into a crater on the south pole of the moon, which you see here. This is called the Cabeus crater. Okay, that is the whole crater that you're looking at over here. Part of that crater is permanently shadowed. That is, it never sees the sun. And the reason is because of the orientation of the moon with respect to the sun, its south pole doesn't get a whole lot of sunlight. That is, the crater regions don't get a lot of sunlight. So these craters have been in darkness for millions of years, maybe tens or even hundreds of millions of years. We know from orbiting satellites now that the temperature, we've measured the temperature from space of these craters, is only about 35 to 40 degrees above absolute zero. These craters are some of the coldest places. In fact, they may be the coldest place in the solar system, even colder than the surface of Pluto, because Pluto does rotate and gets different amount of sunlight, and that is not true in this case with these craters, so very, very cold regions. So this spacecraft was guided into the Cabeus crater, and what you're looking at is, you see this little fuzzy patch right here? And that's blown up right here. So that's that same region now blown up. See this fuzzy patch? What that is the debris from the impact that was uplifted as a result of this collision. That expended upper stage was traveling at over 5,000 miles an hour. So it has a lot of what we call kinetic energy hit into there and released what is equivalent to thousands of pounds of TNT. And that upwelled material that you see over here, this little spacecraft, LCROSS, flew through it and sampled what it was made of. Okay? What did we find? Well, water, and quite a bit. The moon, unlike what most people thought for many, many years, the moon, at least in these craters, has a substantial amount of water. Here's the principal investigator of the LCROSS. His name is Anthony Colapreti, and I mention in particular because he's a PhD from our place at the University of Colorado. He now works for the Ames Research Center in California. Indeed, we found water, and we didn't just find a little bit, we found a significant amount of water. By mass, we think there's something like 2%, maybe as much as 7% of the mass of this debris material is made up of water. Further sensing with radar on the LRO spacecraft indicates that many of these craters in the south and north poles appear to have water. And the estimates now today indicate that there are millions of tons of water within these poles. So that's an exciting discovery. It's exciting because it's a game changer as far as human exploration is concerned. Now going to the moon means we have a source of the most precious quantity right there on the moon itself, namely water. That water, of course, we need to live, but we also break the water up into its hydrogen and oxygen. Oxygen for us to breathe, hydrogen and oxygen also to use for rocket fuel. So we could mine the fuel to return back to the Earth. And lastly, the water is also a very precious commodity to shield astronauts from the radiation that comes from the sun. So a couple of meters of water in a tank over the habitat could be very, very important. The money that will be saved in not having to bring all of that water to the moon is going to be enormous. It is a game changer. The other way it's a game changer is because NASA has said that the eventual goal is to get to Mars. But as I said a little bit ago, Mars is a tough place to get to and to live off the land. You have to, in fact, live off the land from day one. The moon is a great place now with water there, as well as we know there's water on Mars. We can learn how to harvest that water in an environment that's pretty close by. So this was listed by a number of science publications as the #1 science discovery of this last year. So the old moon still has a lot of secrets to reveal. So there's a lot going on. And the interest in the moon just has continued to develop in terms of the science, and it's coming from a lot of different places and areas. But one of the things that the companion spacecraft called LRO, the Lunar Reconnaissance Orbiter, has done is begin looking now in more detail and doing some imaging from orbit of some of these craters. Here's another one over here. Here's another crater called Shackleton. Anybody recognize that name? Shackleton? So famous Antarctic explorer on the Earth, so it's appropriate. He is a crater on the south pole of the moon named after him. The crater itself is in permanent shadow. The rim, though, because it sticks up above the surface, is actually in permanent daylight. Ooh, that's nice, because that means you could use solar arrays all the time to power your base. So one of the ideas is to actually put a human outpost down over here. You're very close to the shadowed regions where the water would be, and you have permanent sunlight for an outpost. Let me show you some video that was made by the LRO of this region, which is very impressive. We're going to do a zoom in here. Here's the rim of the crater in the dark region. So this is going to zoom in here. It's almost like you're right there, isn't it? Boom. Okay. Resolution is 1 meter here. So 1 meter, you know, it's about yay big or so. And for years and years, the resolution of our best pictures from Mars were higher than anything we had on the moon, if you can imagine that. It just shows you how much we've neglected the moon. You can see individual boulders here about the size of this table. This is 1,500 meters from end to end, just to give you some idea of the scale. Looks pretty smooth. A lot of places you might be able to easily locate an outpost and get around there. And here, just once again, you can see a little bit of the shadowed region over here. So it's a great potential location for a future lunar base. And so that is becoming more and more exciting. And so, you know, the excitement does continue to build with these unmanned spacecraft that have been there, interest from a lot of different areas. You know, I just... yeah. You know, when the governor of Alaska resigned as governor, people were asking, well, what is she going to do? And there's, you know, a lot of folks say, well, she's going to run for, you know, president and so forth. But no, she wants to be an astronaut. I mean, it's right here. You can see. And I know there's a number of folks in different locations that would just love to see her go to the moon. And it's just, you know, and of course, there's a number of other people we would like to send along with her to the moon. But you know, that's another story. So. Well, what I want to do from here is to focus more on the science, this continuing growth of the exciting science discoveries. There's so much more. This library book that I mentioned of the moon that we're beginning to open up. And that really is the goal of the NASA Lunar Science Institute, is to study the moon and its relationship to the Earth. The Science Institute defines lunar science in three basic ways. Of the moon, that's investigations of the nature and history, particularly the bombardment history of the moon. On the moon, investigating, for example, the very thin atmosphere and the dust, which is ever present on the moon. And then finally, from the moon, and this is us, this is our center, using the moon as a platform to study the broader cosmos. And here's a highly idealized cartoon picture that we made actually for our proposal that attempts to put together all of the things that we hope to do astronomically and from a physics perspective on the moon. See this green beam that you see coming down over here? This is not the Department of Defense invading the moon, but it is a laser beam. Okay, it's a green laser, and what it's used for is to bounce off of mirrors on the surface of the moon called retroreflectors, some of which were left by Apollo, but we're proposing a new generation that then return back and allow us to measure the distance between the Earth and the moon today to nearly a millimeter, which is incredibly precise. With a new generation of retroreflectors on the moon, we may be able to do a factor of 100 better than that. Why do we want to do it? Because this laser retroreflector is, in fact, the best test of many of the components of general relativity, that theory of gravity that Einstein put together. Why are we interested in that? Because, after all, relativity seems to work pretty well. It's been tested for over almost a century now, and over a century, and has worked extremely well. Well, we know that at some point general relativity breaks down, because the ultimate theory of gravity is going to have to be one that includes quantum physics, that is, what is happening at the atomic and subatomic levels. We don't currently have that. Where general relativity breaks down is going to be very important and insightful in giving us some idea of what the next set of models are going to look like. That's why pushing this envelope as hard as we possibly can is really very, very fundamental as far as our physical understanding of the most fundamental force, gravity, in the universe. I'm not going to have a chance to talk much more about this. Maybe we can take some questions later. Instead, I'm going to focus more on these things that are on the surface, these yellow things you see here. These are low-frequency radio telescopes, arrays of dipoles of antennas that we're going to use to study the sun and also to study the faint whispers of the very first structures in the universe. These are radio whispers at very low radio frequencies. So what I want to do is focus on those goals. And I'll start off by talking a little bit about what NASA likes to call these days heliophysics. That's a fancy sounding term, and it just means studying the physics of the sun. The sun is really quite an interesting place. It's not the calm, sort of unchanging ball of light that we see in the sky. When you look at it in more detail, and I'm going to show you now a little piece of video from the SOHO spacecraft. And what you're looking at here, I'm going to put it in this mode. This is the central region of the sun has been blocked off by this little aperture, and you see these explosions that are occurring on the sun. These are called coronal mass ejections. And they blow off the equivalent of trillions now, with a T, of watts of energy. Okay? Trillions of watts of energy. So enormous amounts going out here in these explosions. And these explosions are associated with regions of intense magnetic field, sunspots, and prominences that are on the sun. But these things are going out and they're producing a tremendous amount of high energy particles, some of which come to the Earth, some of which strike satellites and can do damage. They also interfere with the power grid. And they are extremely deadly to astronauts who may be in interplanetary space, maybe on the surface of the moon, maybe on their way to Mars. So understanding these coronal mass ejections is very important. And it turns out with a low-frequency radio telescopes, it is a powerful way to understand how these high-energy particles on the sun are accelerated up to these tremendous energies. Here's a cartoon picture of the way we think this may be done. Here, once again, the disk of the sun is blocked off, and we can see in white light this piece of a coronal mass ejection. We think it has a strong shock that's located over here. And shocks actually are a great way of accelerating particles. They push things around. You're able to tap in the electrons and the protons and the ions the energy associated with that explosion and transfer it to these very high energy particles. That's a good theory, but this hasn't been tested very well yet because we've never been able to make an image of the sun at low radio frequencies. Turns out those high energy particles, particularly the electrons, radiate prodigiously at low radio frequencies. Here I mean below 10 megahertz. Just excuse me for a second. Just to give you get a little sip of water. Just to give you some perspective, your FM band goes down to roughly 80 megahertz or so. So we're talking about 10 megahertz, so about a factor of 8 lower frequency than that. So these electrons radiate, and if we had an array of low-frequency telescopes on the moon, we could actually take the first pictures of this and ask the fundamental question, or try to answer the fundamental question, how does cosmic rays, or how do these high-energy particles get accelerated, and maybe do a better job of making predictions for the future astronauts to have them protected in space. How are we going to do that? Well, here is our proposal. We got kind of a neat idea for putting an array of telescopes on the moon. What you have to do is, in order to make a picture of the sun at low radio frequency, you have to synthesize a large dish. Well, making a big dish that's maybe a kilometer in diameter is not practical. So we mimic that by putting down a series of individual antennas. Okay? Well, that means we have to put down quite a few onto the surface of the moon. How do you do that practically? And also take into account that we need to keep the mass down. Okay? So we're going all the way to the moon. This has got to be lightweight, and it's got to be easy to deploy. So what we've done is we've come up with an idea of using this thin polymer material, a film called Kapton, and embedding them with metallic antenna elements, rolling them up into rolls like this, taking those to the moon, and then when we get to the moon, either by astronauts or by robots, we simply put those rolls down and unroll it like a carpet. Bing, 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 bing. You've got your individual antenna elements come out like this. And so this is a fairly lightweight way of doing this. The polymer material it's basically a kind of plastic material, and
Ben,
we know what Dustin Hoffman was told about plastics.
Ben. Mr. McGuire. Come with me for a minute. I want to talk to you. Excuse us, Joanne.
Of course.
Thank you.
Oh, he is
It's just I look at him and I can't believe it.
I
simply can't believe it.
I just want to say one word to you. Just one word.
Yes, sir.
Are you listening?
Yes, I am.
Plastics.
So, Bobby, I just want to say one word to you. Are you listening?
I am listening.
It's plastics.
Plastic.
That's how we do our radio telescopes on the moon. It's all about Dustin Hoffman knew that in 1967, or at least he was told the secret. And it was just advanced information, you know, so kept that going. So these materials that we're looking at are lightweight. We're experimenting with these in the laboratory. And we're also experimenting with ways of deploying this. And I want to show you a little piece of video, kind of neat. We have been working with a high school robotics class in Thomas Jefferson High School outside of Washington. And they've been experimenting and building a little device that would put down this dipole film. And I want to show you what they've done. They actually made a little YouTube video out of this, which is kind of neat. And there's their robot, guiding it along here. Not too different than some of the robots that are being built here at IHMC.
No, in the... Wait, don't we...
Here's the roll right over here.
Is it okay?
No, we might as well.
These are high school students now that have built this, okay?
Do you have a bus?
And there we go. There is our antennas.
Yeah, count the bit. I mean...
Now, of course, in this case,
How
it's
many
aluminum
antennas are
foil,
there?
but that's all right.
I gotta go now, alright?
Stop.
We've done that, and
You got it.
control it
Go
remotely
around.
to put down the film,
obstacles that you didn't even
run around.
put there
They've
are
guided
there.
it around here. This is a high school class.
So many
This has
obstacles.
done this. And it's a very lightweight little
doesn't go
robot
any
vehicle
faster.
to be able to do this. And it's amazing. I mean, what's fun about this project
Told me if I ride on the back.
is that not only is it great in terms of the science we can do, but it's been very engaging for many of the students that I've had the pleasure to work with at Colorado as well as elsewhere around the country. You know, one of the things that we're trying to understand is, will this film that we are talking about, this Kapton film, hold up on the surface of the moon? Because Robert Heinlein told us in 1965 in his classic science fiction book, "The Moon is a Harsh Mistress." Sounds like I'm trapped in the 1960s today, doesn't it? I hope not. It's harsh because the day to nighttime temperature on the moon varies from 100 degrees Celsius during the day, that's the equivalent of the boiling temperature of water on the Earth, to minus 150 at night. There's little atmosphere, so it gets very hot and very cold. Gets exposed to extreme ultraviolet light during the day, cosmic radiation, micrometeorite bombardment. So this is a really harsh environment. So one of the things we've been doing at Colorado in my lab is to begin testing this Kapton film in a vacuum chamber to try to simulate the conditions that occur on the moon. So with 3 undergraduate students, we built this little vacuum chamber that you see up over here and put an ultraviolet light over here. These are turbo pumps and so forth. And inside, we've placed a little piece of this Kapton film and went through the equivalent of thermal cycling and exposure to ultraviolet light, and then looked at some of the data, which I won't bore you with the details, other than to say, so far it's held up pretty well. And here's some pictures of 2 of my students, Ricardo and Laura, standing in front of our new larger vacuum chamber that we've moved to. And I said that this is a wonderful training opportunity for high school students, undergraduate students, graduate students, postdocs, faculty members, all of us involved at different levels in this project to think about how are we going to put these antennas on the moon. Well, that initial testbed array that I just showed you that would be used to look at the sun, what we want to do eventually is to put a large array made up of thousands of dipoles on the far side of the moon. Why do we want to do that? Well, it turns out that there is one of the most exciting cosmological experiments that one can do at these low radio frequencies. By cosmological, I mean studying the very early universe, the first whispers of structure from the very early universe. Let me give you a quick tutorial of the evolution of the universe here on one slide. Okay? You've got here, the Big Bang is up over here. Time flows down this way. Here's today, and that's about a little less than 14 billion years since the Big Bang. At about 400,000 years after the Big Bang, there's something called recombination. That's when the first electrons and protons come together and form hydrogen. Now, after that point, the universe is pretty simple. It's got simple atoms, hydrogen, a little bit of helium, a few other trace elements, but no stars have formed yet. There's a lot of action going on because gravity is pulling these little overdense regions together, and they eventually will form stars, but it takes a long time. It takes close to 1 billion years to form the first stars. So astronomers have called this the Dark Ages. Ooh, okay? Because there's no light. All right, there's no stars, there's no quasars, there's no galaxies during this time period. But then the first stars turn on, they blow off, they go through a supernova, blow off a lot of hot gas, heat the surrounding material, and that forms these blue bubbles of hot gas that you see here. This is kind of a geometrical progression, and as you get more and more and more of these happen, till finally you make the last phase transition that occurs in the universe. This point, the universe is all neutral hydrogen. Beyond this point, it's all ionized. That is, the electrons have been stripped. Okay, so you've gone from relatively cold to relatively hot. How exactly did this phase transition occur? The cartoon picture I've showed you over here, it looks pretty straightforward, but we've never observed in this region. Let me show you just a little bit more of how this works. I'm going to show you a supercomputer simulation that one of my students, Sam Skillman, and I have been working on recently, and it shows you the evolution of structure in the early universe. What you're going to be looking at is a box that's about, 100 million light years on a side, okay? And this first image that you're looking at is when the universe is very, very young. It's only about 17 million years old. Now remember, I told you today the universe is about 14 billion years old, okay? So this is a very early stage of the universe. Well, you look at it and says, I don't recognize this universe. This doesn't look like anything we see today. So the question is, how did we go from this to this structure-rich universe that we see today? Well, when you look at it, you notice this is not quite homogeneously smooth, is it? You see some regions over here. This is gas density that you're looking at. It's a little bit denser over here. The black is lower density. These small differences in density over time get amplified by our old friend gravity. Gravity is a wonderful thing of pulling things in together and forming structure. So what we can do is we can put this information into a supercomputer, turn it on, and let gravity do its thing. So let me show you how this, according to these models that we have, and this is written with a very sophisticated code that contains about 200,000 lines of computer code to be able to do this. But what you're looking at here is both time evolving as well as the box spinning around. And you'll notice that fairly quickly, this box begins to change. You see these green regions in here, you get filaments. The blue regions are empty regions called voids. And as time goes on, the filaments get denser. The regions that where the intersection of the filaments occur, these are called clusters of galaxies. There's where the first galaxies and clusters form. And so you end up with a structure-rich environment starting from the very early seeds in the dark ages where we think this works. How do we know that this model is viable? Is because the end product, when this is done, we then compare it with what we see in the actual universe today, and the match is pretty good. Okay? But our problem, as I mentioned before, is we actually don't have observations of those dark ages, at least not yet. What could we see in the dark ages? Remember what I told you was that in the dark ages over here, after recombination, we have hydrogen. And that hydrogen starts collapsing in those overdense regions, eventually forming stars. So there are some regions that are denser and other regions that are less. Well, here is a little view of that hydrogen and how that may change near this reionization epoch. Here, yellow represents neutral hydrogen, and red represents ionized hydrogen. And according to this model, what you see is you begin to see a few bubbles forming. This is where the stars go through the supernova and blow up. You get a few more, a few more, a few more. Notice these regions start merging, and then it's kind of like a fractal, okay? A little bit of growth this way. And then when you get over here, at about this time period, about 1 billion years after the Big Bang, then our universe has gone from being all neutral to all ionized. So in principle, we could see this with the hydrogen. Okay, that sounds interesting. Can we see the hydrogen? The answer is yes. Nature has provided us a way to view the hydrogen. Here, and don't get too scared. This energy level diagram as you're looking at here, because we're gonna make this understandable. Here's hydrogen, really simple. Here's a proton. Here's the electron. Okay, and you might remember your physical science that you studied that the hydrogen atom has energy level diagram, has energy levels. The N equals 1 is the ground state, and there's an excited state. Well, it turns out that this ground state of hydrogen is a little more complicated than that. It actually is subdivided into two other energy levels that depend upon the spin of the proton and the electron. When their spins are parallel, that's the high energy level. When they're anti-parallel, that's the low energy level. And the difference in energy between those levels, that produces a photon, and that wavelength is 21 centimeters. It's a very famous number, any of you that have studied a little bit of astronomy. That corresponds to 1,420 megahertz. Okay, so you can observe hydrogen. In fact, we do this all the time. We observe hydrogen, neutral hydrogen in our galaxy. Now, if you go back into the early ages that we're looking at, that is what are called redshifts, what's happened is space-time itself has stretched, okay, according to Einstein. And as it stretches, it also stretches the wavelength of the radiation. So it's stretched to longer and longer wavelengths, which mean lower and lower frequencies. So that when you get out to a redshift of 10, which corresponds to, about 50 million years ago, 50 million years after the Big Bang, you're down to 130 megahertz. When you're right in the middle of the dark ages, that corresponds to a frequency of 30 megahertz. So you've taken this neutral hydrogen, which is in the laboratory, its frequency is pretty much what your microwave oven runs on, and you stretched it way out, so now it's at very low radio frequencies. Okay? Fine. This says we should be able to see this. We should be able to go look for it. The problem is it occurs at a part of the electromagnetic spectrum that is a mess on the Earth. It's polluted beyond belief. Okay? We've done this to ourselves, but also we live with this ionosphere above our head, which makes it difficult as you get down to the lower end of that frequency band to have the radiation pass through from these cosmic sources to our telescopes. So it's very hard to do this from the Earth. Okay? Just another cartoon picture of that evolution of the early universe. Here's the Big Bang over here. Here are these first stars and the bubbles of hot gas as they blow off. They're supernovae, and eventually these bubbles merge together, and you produce this transition between the all-neutral to the all-ionized universe. Again, cartoon picture. We want to observe this to see if this is actually what happens. Thus, the moon. Why the moon? We want a destination moon. Remember that movie we talked about from 1950? Destination moon, okay? Because it is the place in the solar system where the far side of the moon does not have this radio interference. Well, you say, how do I know? Well, I know that because NASA actually sent a spacecraft in 1973 to orbit the moon with a low-frequency radio dipole on board. It's called the Radio Astronomy Explorer satellite. And here is the actual data. This is, think of this as kind of flux over here, or signal versus time. Here is the signal when the Earth is in view. Noisy, a lot of stuff, because even in space, the interference from the Earth, as well as natural processes, propagate out. Here is the spacecraft when it was above the far side of the moon. Nice and flat, sort of right down to the theoretical level. So we know that the far side of the moon is radio quiet, so it's a good place to go. So what's our plan then? We want to build this in stages to do this cosmological experiment. We've actually started off on the ground, and my colleagues are working on a series of small ground-based individual telescopes or arrays, mainly in Western Australia, because that's one of the most radio quiet places on the Earth, but also operating at the higher frequencies, that is from 100 to 200 megahertz, where it's more practical to observe. So you don't really probe the dark ages, but you get to look at the end of the reionization in here. That's step number one. Step number two is, in this decade, we're proposing to place a single antenna in orbit of the moon at low radio frequencies and observe the all-sky signal, which is expected from this epoch of reionization of dark ages. And here's the prediction from our models. We're going to test that with a simple single dipole antenna in lunar orbit. And that's able to differentiate between when the first stars form, when the first black holes turned on, tremendous amount from this simple experiment. And then eventually, sometime in the decade of the 2020s, is to place an array on the far side. Here you're looking at the crater Tsiolkovsky, which is on the far side of the moon, and an array of thousands of these antennas. Maybe the antennas will look like these capped-on film antennas that I was showing you before that we're going to deploy like a carpet. Or some of my colleagues at MIT are looking at another form of these antennas, and I'll show you a little movie of what they've come up with for an alternative. Kind of put down a pizza box, very thin, gets to the moon, opens up like so. Central region comes up, pops up like so. Got lots of moving parts here. And at the very end, bingo, these helical antennas would pop up. They would operate in much the same way. So what you would need is a little rover vehicle that would go out and pop these pizza boxes down on the moon. Again, thousands of these in order to be able to do that. So this is an alternative that we're studying, and we're going to do a shoot-off on this eventually. Okay. So lastly, to conclude, we're also looking at, with other colleagues, other possible astronomical telescopes that would be enabled by a return to the moon, large rotating optical telescope, cosmic ray telescopes, and telescopes actually in space that are brought into space by a new heavy launch vehicle that we would need to get to the moon and place our telescopes on the moon, but also could deploy telescopes in space. Let me show you a little video of this, because it also gives you some idea of what this heavy launch vehicle, heavy lift vehicle would look like. Okay, so this has got a little audio associated with it, and a little theme music is kind of exciting. Give you a little inspiration here. This was the Ares 5 version of a heavy launch, heavy lift vehicle. That has a couple of strap-on solid rocket boosters like the shuttle, in fact derived from the shuttle, as well as liquid hydrogen oxygen engines that are similar to the Saturn V. But this has 50% more capability to bring mass into space. We cannot travel outside of Earth orbit without a vehicle like this. We must build this rocket. Maybe not exactly like this, but something that has that capability. This is the future of human exploration as well as science.
Copy. What is your shutdown plan? Shutdown plan is nominal. Copy.
So like the shuttle, these drop into the ocean and can be recovered and refurbished.
And flight final. Trend with -2. Nominal margin is only 7 feet per second from what we predict.
Second stage is Apollo-derived technologies on the engines.
All vents open. Copy vents. Flight to pitch is stopped. Got up to about a little over 3 degrees a second.
The shroud comes off to reveal the telescope. 10 meters is the diameter of the shroud. Huge.
Let's see, guidance on 5. We're going to be using the board.
Did you hear me? It was huge. And here's the telescope. In this case, we're not going to put it on the moon. but we'll put it in what's called a Lagrange point. That is a balance point in space that's actually beyond the orbit of the moon, because it's a really good place to observe. It's nice and quiet and cold and stable. So this shows you some idea of where that is. So here's the Earth, here's the moon, and the orbit will be right out over here. Telescope, you know, the solar panels are unfolding. This is a single aperture ultraviolet and optical telescope. This will be the true successor of the Hubble Space Telescope, because it would operate in the same wavelength band. And you can see the aperture mirror. This mirror would be 8 meters in diameter, is the proposal here. Study the very early universe, active galaxies, look for protoplanets, or exosolar planets, I should say. So you feel inspired? You ready to go to the moon? Because the moon sent us a Valentine back just a couple months ago from LRO, and here it is. Let's go to the moon. Thank you all. I think we've got some time for some questions, and maybe we could have the house lights all the way up, and we've got some microphones in the coming back around here. So anybody have any questions that you would like to ask? Okay, let's start right here where we've got a mic that's handy, and speak up nice and loud so everybody in the other room can hear you.
First of all, I want to thank you for an excellent presentation. My name is Joe Edmiston, and I'm asking if this will be a manned mission or not, and if it is manned, will they try to produce plants and photosynthesis?
Joe, those are all good questions. Our science experiment on the moon, particularly the radio telescopes, are designed to go with either humans or probably with robot vehicles in the short term. So our telescopes don't depend on having humans back on the moon. But there's certainly, as far as geology is concerned on the moon and exploring that aspect of science, humans have already been demonstrated to be pretty key in being able to be more insightful explorers than even our best robots can do today. So it doesn't require it. Going back with humans, though, which will happen, I am absolutely confident it will happen, and we will set up an outpost. Ours is going to require a greenhouse and growing plants and experimenting, you know, in that kind of environment with how well we're going to be able to do that. So there's some good science exploration to happen right there in that environment too.
Thank you.
Other questions? Let's start. Why don't we go back over here to the front? Well, just a second. We'll get the mic for you.
I don't know how wise this question is to ask, but is
all questions are wise questions. So.
Will the dust that's on the moon be available to help with planting on?
Yeah, that's actually, it's a very good question. Where are you going to get the soil? Are you going to bring the soil all the way from the Earth? Well, probably not. So people for years actually have been experimenting with lunar simulant material. It's the dust and the whole regolith. You have to fertilize it. So where do you get fertilizer? Nitrogen, right? There's plenty of nitrogen actually implanted by the solar wind on the moon. So you have to get that out of the soil and fertilize it, water, and go to town. So hopefully, I mean, it's not that simple, but you know, the ingredients are there. Everything's there on the moon. All of the minerals and elements that we're used to on the Earth are in a different form, and they have to be mined from the moon. But in principle, we can get all of those. So we can get the water. There's hydrogen, all the way through to iron and nickel, nitrogen. So there's a storehouse of material there on the moon. Once we learn how to extract it properly. There was another question right over here.
I echo Dr. Edmonds' remarks, and remarkably inspiring. Thank you. I'm Bill Spain. I wonder, have you run this by the Chinese and the Germans so they can help us finance this project?
Chinese are helping us finance everything today, isn't it? The Chinese have designs on their own missions to the moon. They have, as I mentioned before, they have put the first unmanned satellite around the moon. It was very successful. They haven't been yet very forthcoming on sharing the data with the international community. They're promising that they're going to do this. And of course, you know that the Chinese have started a human program in recent years. Simple, kind of reproducing what was done with the Gemini and Mercury missions. But they have a stated design themselves to put humans on the moon at some point. So can we do this? I think the heart of your question is international cooperation. Apollo was all U.S., all funded by U.S. Of course, in those days, it was driven by a very different political era. Today, it makes far more sense to cooperate in whether we go to the moon, whether we go to Mars, whether we go to asteroids, and do this internationally, working with the Europeans, the Russians, the Japanese, which we're doing right now with the International Space Station. That's a brilliant success of the space station is actually having all of these international partners. Maybe the Chinese someday, very possibly the Indians. So that's the way I think we want to explore the cosmos as a community of humans. Let's see, I'm going to make it tough for you all to get into the middle there.
Wallace Hodge is my name. If you're going to put your antenna arrays on the far side of the moon and even that last satellite,
yes.
Since it's a radio quiet zone, how do you communicate back with Earth?
Yeah, great question. How do you communicate back with Earth? You have to have a communication satellite that will either be in orbit, or some folks have been playing around with the idea of putting it at one of these Lagrange or balance points that are part of the Earth-Moon system. It's actually beyond the lunar orbit, so it would sit more or less stationary above the far side, but still be able to see the Earth. But it's essential to have a communication satellite. In fact, several mission designs right now, they're underway for first unmanned landers on the far side will require such a communication satellite right out of the gate. I think we'll see something like that in this next decade, in this decade that we're in right now.
We have time for about 2 more questions.
Okay. Let's, we've got some in the back here. Let's see if we can stretch in the middle again. To you next.
Thank you, Dr. Burns, for a wonderful, informative talk. I just have a question about the moon. From subject matter that I've read, it's apparently drawing away from the planet Earth somewhere around about ½ an inch a year. And I wonder if you could give me the consequential effects of the gravity that would have on planet Earth as it pulls away from Earth itself. And it does seem troublesome to me that it would upset the balance of the Earth and the gravitational pull. Can you help on that?
I can, yes. I can give you some insight. And you don't have to worry. There's a lot more. This has been happening for literally billions of years. Right after the moon first formed, about 4.5 billion years ago, the day on the Earth was only about 5 to 5.5 hours. Okay? And the moon was much closer to the Earth than it is today. There's a fundamental coupling between the spin period of the Earth, that is the day on the Earth, and the distance of the moon from the Earth. As the moon has drifted further out, the Earth has slowed in its rotation. So, of course, today we've got a 24-hour. I mean, we think of that as immutable, right? Not at all. Nothing's immutable in the universe. I mean, things change, but just on time scales that are a lot longer than human lifetime. So this is a process that's been occurring. It's part of the conservation of angular momentum theory, that or practice in physics that we have. So it's been a long-term effect. But you can imagine what it must have been like billions of years ago, in that the tides were stronger on the Earth as the result of the moon being closer. And so that was the beginning periods where life formed on the Earth. We think life happened within 1 or 2 billion years after the formation of the moon and the Earth, and so life formed in that particular environment. Was that crucial for the formation of life? I don't know. I mean, there are many such interesting questions we'll yet to define. So, very good question, though. Another last question. She's been waiting very patiently. So,
very good lecture. Thank you. I was so excited to hear you say fractal. I mean, I looked at that.
I heard you shout out at that one.
Because I was already looking at that one picture where you were showing it to begin to form, and I had a thought, and I just said, well, what if you laid a fractal over that vacant, empty energy spots, more energy spots, and so on, and the creation starting, and then the heat coming from that, and what if you laid a fractal over that, and then could you measure the empty and the full? You know how they do a forest, and they measure the big and the small tree?
Yeah, you can do that. You can apply those kind of statistics, and they have been for both of these kind of models. Fractals are ubiquitous in the universe, everything from snowflakes to the large-scale structure of the universe. So they're a very common mathematical form. So, but you can use that mathematics to try to understand how these structures then come together to eventually merge all of the ionized region and produce the reionization.
I was going to say. So then the creation of all the galaxies and things started.
That will result from that.
That's great. Thanks.
Please join me in thanking Dr. Burns for his visit.
Well, thank you, Ken. Thanks for that generous introduction, and good evening to you all. It's wonderful to be here in Pensacola. This is my first trip to Pensacola, and I was looking very much forward to it when about 6 months ago Ken invited me to come and visit with you all. I've been very impressed with the city, with this institute, and the friendliness of you all here. It's been great. So I do have some southern roots, so they'll come out now and then. Well, tonight what I'd like to do is to tell you a little bit about our new center that we have developed called LUNAR, the Lunar University Network for Astrophysics Research. About 2 years ago, NASA formed a new institute itself called the NASA Lunar Science Institute, and it's located in the Ames Research Center in Palo Alto, California. And in turn, they put out a call for proposals about 1.5 years ago for university affiliates or university centers. Very high, stiff competition, see it. So, of course, we did go to the moon successfully. In 1969, we fulfilled John Kennedy's vision to go to the moon and return back safely by the end of the decade. He proclaimed this in 1961, just literally weeks after Alan Shepard's first suborbital mission. It was astounding vision that was set forward and the technology leap that was required to get there. But indeed, in 1969, we celebrated the 40th anniversary just this last summer, set foot on the moon. Here was the landing vehicle that I've superimposed above the surface of the moon. A couple of the astronauts on their lunar buggy, one here. And this is Jack Schmitt. I show this picture because Senator Schmitt, who's actually, when he finished off, became senator from New Mexico, was a PhD, is a PhD in geology, the only scientist astronaut to go to the moon. I think people understand certainly that Apollo was a great success in many different ways. Number one, of course, it was a political success. The idea was to beat the Russians to the moon. It was the middle of the Cold War. That was successful. The second way that it was successful is that for human exploration, we broke the bonds of low Earth orbit. and went in just a few years all the way to the surface of the moon and stepped foot on another astronomical body. Clearly, that was a pioneering breakthrough that we have not duplicated. Never seen this kind of women before. Without men for centuries. How do they procreate?
Where are your menfolk?
You're the first man I've ever seen.
3D. Okay, James Cameron, he thinks, Avatar is special on 3D in 1953. Look at the interior of the spaceship. They're supposed to be in 0G, but they don't seem to be having trouble putting the makeup on there. And of course, the Hollywood cover girls. Who else would you choose?
And what's the matter?
Danger, Kip. They want to kill you. They'll take the spaceship and they'll make me go with them.
Great acting in here, too.
They can, Kip. They control me.
You'll share man's greatest thrill as you rocket through space to the lost moon city of alluring, ferocious cat women. Theirs is the fevered fury of life without love, goading them to lure men into the den of bloodthirsty moon monsters.
We missed those with Apollo.
To tempt men in the
I bet they are hidden
cave
underground
of moon gold,
somewhere in these
flaming
lava
into a
tubes.
wild lust to conquer man and
That's gonna leave
destroy
a
the
mark.
world.
Yikes. Oh, rough. It's the most startling picture of the century. I believe that's true. Wow. No, I don't know how many of you have seen cat women. You probably don't remember if you didn't. We were fortunate to be one of the 7 university centers that was chosen, and we're the only one dedicated to the pursuit of astronomical observatories on the lunar surface. And so what I want to do tonight is to tell you about some of the unique facilities that we are planning, both in the short term as well as the longer term, on both the near side and the far side of the moon. Ken mentioned that our lunar facility is headquartered in Boulder at the University of Colorado, but very importantly, you see the logos down over here. These are the many institutions that are affiliated with us. We have over 40 individuals from places, NASA centers such as the Goddard Space Flight Center, the Jet Propulsion Lab, Harvard University, MIT, UCLA, the National Radio Astronomy Observatory, and the Naval Research Lab, just to mention a few who are involved in this work. Well, humans have been interested in the moon probably as far back as folks started looking up in the sky and wondering what that big bright ball was hanging there in the sky. It's far and away the brightest object in the nighttime sky. It's the only one that you can really resolve well with the human eye. Classic science fiction has been written about the moon. You go back to Jules Verne in the 18th century, 19th century I should say, 20th century you had H.G. Wells. And beginning in the 1950s, there was also some really interesting science fiction movies that began to appear about the moon. Here is probably one of the best, I think. This is called Destination Moon, 1950, 60 years ago. People were talking about trips to the moon, and here's just a couple of frames from that movie, and really not too bad of a job in capturing some of the features and so forth. What they did miss is the fact that on the surface of the real moon is about 2 centimeters, a few inches or so of dust, which is present everywhere on the moon, and probably is the kind of feature also that you will see in asteroids when we eventually get there as well. So a number of such movies, some fairly serious like Destination Moon. Others, well, not quite as serious. Catwomen of the Moon, 1953. You've never seen anything like it. That's probably true. Love-starved moon maidens on the prowl. Here's something interesting. Music by Elmer Bernstein. Anybody recognize that name? Yes, he composed some Academy Award-winning music. Not in this movie. He was clearly slumming when he was doing this. I actually have a little clip for you of this movie that I want to play for you. It's a trailer for the movie in 1953. Just kind of fun to take a look at, see what we were thinking.